What the heck?
Togon.
Howdy, partners. It's a little dark in here. Let's change that. That's a bit better. It's a rainy, rainy day. So last week I did not put out a video because it was my birthday. Hooray! Now I'm the ripe old age of 24. Today we're going to start on something that has been recommended to me as something that I cover quite a bit, and that is introducing the most generalized function that one can really, or you know, just about as general as you can get with functions, and that would be the hypergeometric function. Now this is a rather, I would say, somewhat obscure aspect of studying functions, and I guess you could call it functional I guess just analysis is what this is part of, but we can't just jump right into it. We sort of need to introduce a particular topic, and that would be the rising and falling factorials. So let's talk about that today. That's our subject. That's what we're doing. Watch it. Enjoy it. Math. I figured perhaps today we would try a slightly different format. This time it's actually teaching, because I'm completely on camera and you get to look at my beautiful, beautiful visage for the entire video. So today we're learning about rising and falling factorials. Now what the heck is that? Let's go with the purple for the rest of it. So rising and falling factorials is sort of like an incomplete version of factorials. Maybe there's an analogy to the incomplete gamma function, maybe? I hadn't thought about it. But they're pretty easily defined, and I'm going to be using Knuth's notation. Donald Knuth. I think is it Knuth or Knuth? I don't know. It's kind of funny to say it like that. It sounds like a German name if you say Knuth, like Knie or Knife. But they're pretty simple. It's like an incomplete factorial. So Knuth's notation is you write x with like a power of n, but you put a little bar above it if you mean the rising factorial. And the rising factorial is you start with x, and you multiply by x plus 1, and then x plus 2, and you just keep going until you get to x plus n minus 1. Right? So you go all the way up to there, from x times x plus 1 times x plus 2, all the way up to x minus 1, plus n minus 1. And so this is pretty easily seen to be the product from k, sorry, this is sort of on the fly, k equals 0 to n minus 1 of x plus k. Right, so we're just sort of multiplying from x plus 0 times x plus 1 all the way up to x plus n minus 1. And the falling factorial is sort of just the opposite of that. So x, and then you do the little power of n, but the bar underneath it. And that's just simply x times x minus 1 times x minus 2 all the way down to x minus n minus 1. I guess I'll put n minus 1 in parentheses there to sort of make it the same as this, so I don't have to distribute the negative at all. And of course that's defined as the product from k equals 0 to n minus 1 of x minus k. And I just realized something. If you multiply them together, you can write this product together as the difference of the squares. That's interesting. So I just realized that. I didn't actually think about that before, but if you multiply the rising factorial by the falling factorial, you get the product over the difference of the squares. So k equals 0 to n minus 1 of x squared minus k squared, because x plus k times x minus k is x squared minus k squared, right? That's the difference of the squares. And now that's an interesting little identity. I had not thought about that, but that's neat. So that's just one thing I noticed. So why are we even talking about this? So rising and falling factorials are relevant, are relevant to something called the hypergeometric function, which is a construction that's used to try and sort of generalize all functions into like one group. And there's the generalized hypergeometric function, and it really gets quite abstract and as general as you can really possibly be. And it's sort of a way to how should I phrase this? It's sort of a way to get all the functions in like one place, under one roof, all the neat functions, you know, that we all care about, like exponentials, or trigonometric functions, or logarithmic functions, or polynomials, right? These are all just polynomials. So if I picked like if I picked n to be, you know, 3, then we stop right there, and we just get x times x plus 1 times x plus 2, and that's just a polynomial. You know, and we get different values depending on which n we pick. There are some neat identities we can derive. Of course, we want the empty product, so anything that's 0 rising factorial is going to be the same as 0 falling factorial is going to be 1, right? It's the empty product, like we're sort of used to with factorials. If you do 1 rising factorial n times, that's going to actually be the same thing as n factorial. And it's not too hard to see from the definition, right? We plug in 1 for x, and we get the product from k equals 0 to n minus 1 of k plus 1. So we could sort of move the indices up by 1, and we'll see that we could do the product from k equals 1 to n of just k, which is n factorial. Likewise, we can write this in terms of the falling factorial, and that's actually just going to be the nth falling factorial of n. So I guess I would read this as the nth falling factorial of 1, the nth rising factorial of 1, and the nth falling factorial of n. And so those things are precisely all the same. And of course you can write these things in terms of the gamma function, which is just, you know, gamma of n is just n minus 1 factorial. I took some notes just so I would know what to say. There's some neat little identities we can derive. So let me get my eraser. For example, if we take a look at the falling factorial, we see that this is almost x factorial, except we stop because we remove everything from x minus n downwards. So falling factorial is actually, the nth falling factorial of x is actually x factorial divided by x minus n factorial, because we're sort of removing this stuff from the bottom. But of course this is really close to x choose n, right? So if we just multiplied x choose n by n factorial, you see that we get the same thing, right? So x choose n would just be x factorial over x minus n factorial times n factorial in the denominator. Since there's no n factorial in the denominator, that just means we've multiplied the n factorial over. So we can multiply x choose n times n factorial, and we get the falling factorial. We can do a similar thing with the rising factorial, because we can write it as this factorial minus all the stuff that comes below it. So the rising factorial, or the nth rising factorial of x, can be written as this factorial, so x plus n. I guess we could write it as, since it looks more nice, we can write it as x minus 1 plus n. X minus 1 plus n factorial divided by x minus 1 factorial. Because if you think about it, we're going from x to x plus n minus 1, but there's all the stuff below it. So there's x minus 1, x minus 2, all the way down to 1. So we're dividing by x minus 1 factorial. But of course we can also do a similar representation of this in terms of the choose function, which are also the binomial coefficients. And we're also just missing n factorial in the denominator here, so we get n factorial times x minus 1 plus n, choose n. And so these are also ways to express the the rising factorial and the falling factorial in terms of previously understood things like the choose function and the regular factorial. So these are just some identities that we're deriving, and remember this is just an introductory video on this topic that we're going to use to explore the hypergeometric function in the next video. I wanted to try this format, see if this works. If this isn't preferred, feel free to tell me in the comments. I'm just trying something new. I felt it might be interesting to do more of like the lecture style where I'm always on camera as opposed to you just seeing my hands. But let's see how this bears out. So what's another identity we can do? Oh, there's neat ways to represent these things in terms of each other, right? So that's neat, right? We can somehow represent this in terms, we can somehow represent the rising factorial in terms of the falling factorial, and vice versa. So let's see that in action. So I'm going to erase the definitions now. It seems sort of obvious what we're talking about now. Hi there, it's me from the next day, and I wanted to derive one more little identity that is not going to appear in the rest of the video because I just realized it while I was editing the part that you were just watching. So we showed that the falling factorial is precisely equal to x factorial divided by x minus n factorial. And we showed that the rising factorial was equal to x minus 1 plus n factorial divided by x minus 1 factorial. But notice, these sort of look similar, right? They sort of look like they could be, oops, there's a glare, give me a second. But these sort of look similar, like they could be related somehow, like we could somehow manipulate this into that. And we actually probably can. So what I'm going to do is I'm going to factor negative 1 out of all of this, so that's going to become 1 minus x, and that's going to be minus n. And I'm going to factor negative 1 out of all of those, 1 minus x. But that many factors of negative 1 is just this amount, so we end up with negative 1 to the power of 1 minus x minus n. And here we get negative 1 to the power of 1 minus x. But of course, this many negative 1s cancels with this many negative 1s, and we're left with negative 1 to the power of n, which is the same as, we're left with negative 1 to the power of negative n, which is the same thing as negative 1 to the n. So if I rearrange it like that, I get negative 1 to the n as being factored out like that. But now, and nothing has changed. I haven't changed the value of anything. I've just cosmetically altered it. So now I'm going to reciprocate this. So this means that 1 over the rising factorial, of course the reciprocal of powers of negative 1 are just the same powers of negative 1. But now I have 1 minus x factorial divided by, and let me just delineate this, divided by 1 minus x minus n factorial. But notice this right here is just this with 1 minus x plugged into it. So this is the same thing as negative 1 to the n times the nth falling factorial of 1 minus x. And so that's a neat relationship that I did not notice until just now. And so, of course, if you plug in 1 minus x into here and reciprocate, you get a similar relationship. So we can similarly discover that if we reciprocate both of these and then plug in 1 minus x again, we also see that 1 over the falling factorial of x is equal to negative 1 to the n times 1 minus x, but the nth rising factorial of 1 minus x, right? Because if we plug in 1 minus x into there, this becomes the nth rising factorial of 1 minus x. And if we plug 1 minus x into there, this becomes x. Then we just reciprocate both sides, multiply the negative 1 to the n over, and we get these two relationships. So that's another relationship that I didn't notice until just now. So these are the same, and these are the same. Again, you'll see another way that we can write the rising and falling factorials in terms of each other. I just figured I'd share this one that I thought of just now. So this is relating the rising and falling factorials as reciprocals, and so is this. Right? So both of these are more or less the same relationship, so you can really think of this as one thing, and then you're just swapping these, and you get the same relationship. So 1 over the nth falling factorial of x is equal to the nth power of negative 1 times the nth rising factorial of 1 minus x. You can then exchange the rising and falling factorials for the same relationship in that way. I hope that's clear. Oh, no, never mind. All right, whatever. I'm done with this. Just figured I'd add that into the video. Thank you for watching this part, and back to yesterday me. If you forget what the definitions are, refer to earlier in the video. So, let's see. So I'm actually going to end up writing them out one more time. So we have x, the we have the nth rising factorial of x. If we write that out again, we have x times x plus 1 times x plus 2 dot 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 times, is that still in frame? I believe it is, times x plus n minus 1. But we could view this as a falling factorial if we consider this to be the place that we're starting and we're working our way down. So this is also the same as the nth falling factorial of this thing right here. So that's x plus n minus 1, but the nth falling factorial of that, because we just sort of work our way down to there. I hope that's clear, right? It's instead of thinking of starting as x and adding 1 each time, we're starting here and subtracting 1 each time, which is precisely what the falling factorial is. It's a little slanted. It's sort of hard to write straight when you're writing it in this direction. You have no idea which way I'm pointing. This is the third dimension that you don't have, but whatever. So the point is that we can write the rising factorial in terms of a falling factorial. More interestingly is we can replace x with negative x and get a neat little relationship. So let's say we multiply all of these things by negative 1, which means we'd have to divide everything by negative 1 as well. So there's n terms, right? Plus 0, plus 1, plus 2, all the way up to plus n minus 1. That's n terms. So we could multiply by negative 1 to the n, and then just also multiply all of these by negative 1. So we would get negative x times negative x minus 1 times negative x minus 2 dot 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 all the way up to negative x minus n minus 1. Which means that this is really the nth falling factorial of negative x, right? So this is negative 1 to the power of n times the nth falling factorial of negative x. So the nth rising factorial of x is negative 1 to the power of n times the nth falling factorial of negative x. So that's kind of an interesting relationship, right? All we did was sort of multiply by n negative 1s and then also multiply each of the n terms by negative 1, thus canceling out the negative 1s, and then considering this as a falling factorial. And an analogous thing can be done with the falling factorial, right? Because the falling factorial, the nth falling factorial of x, is x times x minus 1 times x minus 2 dot 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 all the way down to x minus n minus 1. Of course, we can then similarly actually think of this as a rising factorial, like we did here, when we're starting from here but going up to x. So of course this is the same as the nth rising factorial of x minus n minus 1. Like that. So of course we can reframe the rising factorial as we can reframe them in two different ways. We can reframe it as, we can reframe the nth rising factorial of x in terms of the nth falling factorial of the end result of the rising factorial, or we could rewrite it in terms of the nth falling factorial of negative x. Similarly, we can write the nth falling factorial of x in terms of the last step, the nth rising factorial of the last step of the falling factorial, or we could similarly write it as in terms of the rising factorial, the nth rising factorial of negative x. So this becomes negative 1 to the power of n times the nth rising factorial of negative x. And so this is a couple ways of rewriting these functions in terms of each other. So those are the same, and these are the same. Right? Cool so far? Just demonstrating some relationships between the two things, relating them to one another. Let's see, is there anything else I had that I wanted to cover today that was sort of just their properties? Oh yeah, sorry, so there are actually some other properties that I wanted to cover. Let's see. So real quick, we can think of the rising factorial, a sum rising factorial, so or a falling factorial. So the m plus nth falling factorial of x. What could that be? Well, we want to think of this as like combining these two things together. So first we can think of it as first doing the mth falling factorial, but then we start at x plus m and go n steps further. So this would then be multiplied by x plus m, but the nth falling factorial of that. So this is the way that you would sort of do a falling factorial sum. I hope that's rather, oops, I'm so sorry. I got that backwards. This should be a minus. My mistake, that should be a minus. And then if we did the same for the rising factorial, but a sum, right, like that, then we have ourselves the nth rising factorial, and then it's x plus m. But the nth rising factorial of that number. So I hope that's clear. We're sort of splitting up the sum into two different parts. This is sort of maybe a defining, how we define the rising factorial in much the same way that we define exponents in this way, right? If we do x to the power of m plus n, now this is just regular powers, right? Just powers, we get x to the m times x to the n, right? That sort of defines what we mean by exponents of things. And where did I put my eraser? And so this is sort of an analogous relationship between those, right? So we're doing a falling and a rising factorial, but a sum inside there, and so we can break it up in this way. Let's see, what else is there to think about? A neat little duplication formula is if we do the 2n rising factorial of 2x. Like that. So we can think of this in two ways. We can think of doing this in terms of the sum, or we can like break it up individually into its own little pieces. But so actually, let's do it through this. So let's use this. So we'll use this relationship to sort of conclude what this is, because what's 2n but just n plus n? Right, like that. And so utilizing this little fact that we've just derived, I'll just separate them real quick. We can rewrite this as 2x, but the nth rising factorial of that times 2x plus n, and the nth rising factorial of that. But now we have a factor of 2, n factors of 2 from here, and n factors of 2 from here. So we can factor that out. We get 2 to the 2n times the nth rising factorial of x, and the nth rising factorial of x plus n over 2. But for some reason, the Wikipedia article for this says that it's actually 2 to the 2n times the nth rising factorial of x times the nth rising factorial of x plus 1/2. Now I don't quite get why that would be the case when we just derived this from the thing that clearly makes the most sense, right? You get the nth rising factorial of x, and then you're at x plus m, and you do the nth rising factorial of that. That seems like this makes the most sense, and I just applied that to this. And yet I get a different answer from what the Wikipedia article says. So this is what I got, this is what the Wikipedia article says, the difference being that this has an n here and this has a 1 here. So I'm not too sure why that is so. But I'm pretty sure this one is right, the one that I derived. So these are just some relationships and ways that we can interpret this new definition of a function and how they relate to each other, and you know, sort of different ways that we can manipulate it and relate these two different functions to each other, the rising and falling factorials. And we're going to get into how they relate to generalizing other functions using the hypergeometric function, and eventually things like the confluent hypergeometric function and the generalized hypergeometric function. And we're going to talk about things like Stirling numbers and law numbers and how they relate to you know, the binomial coefficients, and how you can use regular powers of x, the rising factorial of x and the falling factorial of x, as different bases and do a change of base between them using the Stirling and Law numbers as vectors in their, like polynomial vector field or whatever the it's called. But this was just like a brief foray into how the rising and falling factorials worked. I'm sorry if I'm a little shaky with my words. This is not the exact format that I'm used to. I'm usually a little bit more prepared. I just sort of wanted to see how this would work out. So feel free to tell me how it went. I'm sure I'll get better with this format as time goes on, if I should choose to do it more often. Hopefully I can get a standing board at some point, which I think will be a little less cumbersome to work with, because right now I'm just sitting on my bed. So thank you very much for watching. I hope this was enjoyable. I don't know that there's very many videos about falling factorials and rising factorials and the hypergeometric function, so hopefully this gets noticed. I'll try to put it out there a lot. So once again, thank you for watching, and have a wonderful weekend, even though the weekend is already done by the time this comes out. Peace.